Okay, so this will be just a brief video on matrices as linear transformations again. And we think about multiplying all vectors in the plane by a matrix, and we see how it contorts the plane, like last time. But what we're going to focus on this time is the changes in the area. So we know that a matrix through multiplication can contort the plane, can squish it and stretch it and shear it. And we can keep track of how that affects the area of parts of the plane. That's what we're going to do here. So let's just take this first example here on the left, the matrix 2, 0, 1, 3. And I just want to see what happens with the plane here under multiplication. And what I'll do is I'll start with a unit square. Believe it or not, that's square. I want to see what happens when this square is multiplied by this matrix. I've actually drawn that on Desmos so we have kind of a crisper image. Here's the unit square. Okay. It has area 1. So 1 unit here, 1 unit here, 1 times 1 is 1. And here's what happens when we multiply it by that matrix. Okay, so you can see it stretches it out, doubles this length, it triples this length, but also gives it this shear, moves it like that. Okay, so I want to calculate the area of that red region and compare it to that of the blue region. Well, you could do this multiple ways. One way to do it is you could imagine kind of cutting it here and taking this resulting triangle and sticking it down here. Right? And then the region that we're dealing with is just going to be that rectangle. It's got this side length of 2, this side length of 3. So the area in total is 2 times 3, which equals 6. Okay? That's not strictly what we're interested in. We can see not only the change in that area, but how it might relate to this matrix. So let's find the eigenvalues and eigenvectors. Again, there's many ways you can do this. As we saw when we were live in person the other week, this is what's called a lower triangular matrix. Okay, so all the non-zero entries are in this lower triangle here, and the rest are just 0. Okay, and in that case, the eigenvalues are just these diagonal entries, so 2 and 3. We could also set it up by doing this typical determinant of 2, 0, 1, 3 minus lambda 0, 0, lambda. Okay. Setting this equal to 0, and then solving that resulting characteristic polynomial, as we saw. But if you do that, you will get that lambda 1 and 2, so the two eigenvalues are going to be 2 and 3. Okay? But let's just multiply these together. Okay? So if I take lambda 1 and I multiply it by lambda 2, sure enough, that's 2 times 3, which is equal to 6. Okay? That's not a coincidence that the change in the area of that unit square is 6. Okay? In that the original unit square was area 1, and now the image of it under that matrix multiplication is 6. So it's 6 times the original area. Okay? As we'll see it time and again, this isn't a coincidence. This is like the fundamental property of matrices. Okay? This idea of an eigenvalue and an eigenvector. These are intimately tied together with the change in the area of that unit square or unit cube in higher dimensional space under matrix multiplication by that matrix. Okay? Let's continue with that and look this time at vectors that don't change direction when I multiply it by this matrix. Okay. Again, we'll isolate this problem. I'll save the other one for you to do. Remember how we look for eigenvectors. We set up this equation like this, where v are a vector of unknowns, and lambda is an eigenvalue. When I set this up, we can find the eigenvectors pretty quickly, these v vectors. So I just set it up like this. I'll put v1, v2 for my unknowns here. And I can multiply it by my first eigenvector, or eigenvalue, sorry, of 2, like this. And I can solve the resulting system of equations. And you see I've got 2v1 equals v1. Oh, sorry, 2v1. Got 2v1 equals 2v1. And the other equation is v1 plus 3v2 equals 2v2. Okay. So we can see here v1 can be taken as our free variable, and if you solve that second equation, if I subtracted 3v2 from both sides, I'd see that v2 is equal to the negative of v1. Okay. So I can identify what that vector is going to be. v1 is my free variable, and v2 is just going to be the negative of v1. Okay, so this is my eigenvector corresponding to lambda equals 2. I can do this again with my other eigenvalue, 3. Set that up. Looking for this vector of unknowns here. That is equal to 3 times this. Okay, and when I set this up, I solve the resulting equation. I've got 2v1 equals 3v1. Well, that just gives me 0 for v1, right? And v1 plus 3 v2 is equal to 3v2, and so v2 is going to be my my unknown parameter. Okay, that could be set to anything, and I can conclude that my second eigenvector is this, 0 and 1. Okay, so what this says is that these two directions, this 0 and 1, and this other one, 1 minus 1, these two directions don't change when I multiply all vectors in that plane by that matrix. Okay, so they might be stretched out, perhaps, or compressed a bit, but they don't change direction. They stay in that direction. Okay, we can see that if we go back to our little Desmos image here. Here's one of the directions that doesn't change under that multiplication by that matrix. That corresponded to our 0, 1 vector, so this vector. This whole direction won't change, right? And you can see that with this original unit square and its image, which is this red polygon here. You can see the edges are in, this edge is still in this direction. It hasn't moved away from that axis. It remains on that axis. So that's one of these invariant directions under multiplication by that matrix. It's been stretched out, but it hasn't changed direction. How much has it been stretched out by? Well, by the corresponding eigenvalue. Okay, 3. You can see this has been stretched by 3, but remains the same. Now the other eigenvector is a little more mysterious because it doesn't really show up directly on this red polygon. This is the other invariant direction. Okay, so if I took any vector along here and multiplied it by that matrix, it would still be pointing along this line, but it's going to be shifted, or it's going to be stretched by the corresponding eigenvalue, which in this case is 2. So if I did, for example, let me actually do one of those multiplications so that we can see how it works. So if I took this vector here at 1 minus 1, and I multiplied it by the matrix 2, 0, 1, 3, just quickly do that and see what I get. So 1 minus 1. Shouldn't be surprising what it will be. I've got 2, then 1, minus 3, so minus 2. So it actually becomes this vector here, 2 minus 2. So it stays in the same direction, it's just stretched by a factor of 2, which happens to be the eigenvalue corresponding to that eigenvector direction. Okay, so this is a fundamental observation in linear algebra, which comes up, as we'll see, time and again, that when we imagine matrix multiplication as acting on an entire linear space, it could be the plane like we just looked, or in a higher dimensional linear space, which we'll turn to very soon, we can see how the space is transformed by that matrix. It's stretched, it's compressed, it's sheared, and this and that. There's some directions that don't change at all, and along those directions, we see stretching by the corresponding eigenvalues. Okay. And one other thing to notice is that when we look at just that unit square, or unit cube, depending on the dimension of the space, it's going to be stretched, it's going to be contorted via that matrix multiplication, and the amount it is contorted corresponds to the product of the eigenvalues. So they reveal kind of this change in that fundamental area element in our linear space. Okay, and we'll return to this again, of course, in different contexts, and see that this really is kind of a universal phenomenon in linear algebra.